Next Tuesday we're having midterm. I hope that you guys spend a good amount of time reviewing what we have studied over the last 1.5 months. And if you start with something, you can email me. One advice before you get in the midterm: try to solve at least one question on your own. Try to think freely, having a question that you haven't seen an answer for, and try to solve it on your own, because if you didn't, that means you're not going to do it in the exam. So try to put yourself in the exam mood, having the equation sheet, try to solve the exam. For the exam, you're going to have the equation sheet from the dynamics. You're allowed to have this. And I'm going to send you a fluid dynamics equation sheet that Dr. Leon sent to me, so you can print it and bring it with you to the exam. I'm going to print a few of them just for you if you want, if somebody forget to print them. So that's for you. I told you the exam is going to be 4 questions. 1 fluid dynamics, and 3 on the work and energy and the impulse and momentum. So try to prepare good, right? Okay, so last time we started talking about an interesting topic in the structural dynamics. So let's review what we had. We talked about that there is a building like this, and this building is very, very complex to solve. So the thing is, we try to convert it to a system. It's called multi-degree of freedom system. By the way, all the questions in the final exam that I'm going to ask in this part is going to be 1 question, and it's not going to be a problem. It's going to be just you draw some stuff and show me that you are understanding, like the stuff that I'm doing. Like when I ask you, show me the multi-degree of freedom system, something like this, and how the simplification looked like from a full building to a multi-degree freedom building. And then this multi-degree freedom building has some stiffnesses that are based on the stiffness of this building, like K1, M1, K2, K2, M2. Up to Kn, M, N. Until the final story. The thing is, this system is still complicated. So we try to convert all these masses to 1 mass and 1 stiffness. Okay, something like this, and this is 1 mass. What is the common between these 3 systems? That all of them, if they got exposed to the same earthquake, they are going to have the same performance. Like if this system got exposed to an earthquake and is shaking the base with an F base, and F base is driven by an earthquake that has a time history. We call the time with the ground acceleration. This is the time history of the acceleration. All right? So this is like you put a devices in the soil and keep measuring how the soil is moving. It's going to give you something like this. So if you know the mass of the building and you know the acceleration of the ground, you can know what is the F phase. It's the mass multiplied by the acceleration of the earthquake, multiplied with some bunch of factors. Okay? So that's what we tried to discuss last time. But the thing is, to solve a complex building with a time varying force, F base is functioning T. It's not a constant. Like it's something that every time a step keeps getting changes because the acceleration is changing. So it's really, really difficult problem to solve. So that's why we simplify the building in a multi-degree of freedom, and then do maybe much more or further simplification to get it to a single degree of freedom. All right? So knowing all these simplifications, the thing is, I told you there's one common thing between these buildings. If they got exposed, because they are supposed to be the same, so if this building got exposed to this earthquake, it's going to give you delta like this, and this one delta like this, and this one delta like this. And all of them should give you same delta, because it is same stiffness, same mass. Just like we sum them in a way that can be a total mass and a total stiffness. All right? All right, so how we can get delta? Either from here, here, and here. Thing is, this is very easy to solve. This is the 2nd level of difficulty. This is the highest level of difficulty. So I told you before that this system has a mass and a stiffness, and there's something that we didn't talk about that contribute to this delta. It's called how the performance of this building in damping. Like when a building is is like trying to make a deformation. Sometimes we put some stuff that decrease this deformation. It's called damping. Like it's like a piston. It's called dampers. I'm not sure if you guys went to Google and searched it. It got just open and close to dissipate the energy of the earthquake. Sometimes we put these. And I said this is function in the velocity. C multiplied by V. And the thing is, if we expose this system to this earthquake, let's put it here, time, and this is AG, and this is the earthquake. So the thing is, we need to solve an equation that have some components that resist the hazard or resist the load, and it has the load, right? So the thing is, it's like solving a truss. If you guys remember solving a truss from last time, this is the hinge and this is the roller, and this is something like this. When you solve the truss, you have the load as an input, and also you have the parameters here. You have the geometry, you have the mass, you have the stiffness, you have everything. So I told you, I showed you how the dynamics equation of this structure look like. We found out that the dynamic equation of this function is like something like this: m u double dot plus c dot u dot plus ku equal to the ft. We drew the free body diagram, and we found out this equation. So this equation basically take the building parameters here, and we call this the resistance function, and then take the load here, and we call this the forcing function, and try to find with the resistance and the forcing how much delta that this building is going to have. And delta is, the solution is always u. What is u? This delta is equal to u. What is the value of u? And we said last time that this equation is a differential equation from the second degree and non-homogeneous, right? Because there's ft here, right? Okay, so the final solution u, once you solve this equation, is gonna be something, this u is gonna be something like this. Like the solution, let's put it here. U is gonna be something like this. This is time and this is u. Since the load is function in time, the deformation is gonna be function in time, right? Like if the base is moving that way, the building is gonna make like this, positive. And if it's gonna go like this, it's gonna make negative, right? It's gonna be positive, negative, and sometimes it's gonna be high based on the force down. Like if the force is very low, there's gonna be a little bit of deformation, but once it gets to the peak, it's gonna make like this and gonna throw back. So it's gonna be something at the end, something like this. Something like this. How's the displacement look like? How we can find this? Basically, they divide this curve into a bunch of pieces, and they put each piece here, and they integrate the equation from time 0 to time t to get all this history of displacement. And same way, we can do it to get the velocity of the building. And the velocity is u dot. And same thing, we can do it with u double dot, and the final velocity is going to be also something like this. The final acceleration is going to be something like this. That's the final results once we solve this equation. Okay, we got this. That's all what I have done last time. Okay, all right. I just review it very quick. And also we start talking last time about something that's called the natural period of the structure. Okay, so fundamental. It's called fundamental or natural period. The fundamental period of the structure comes from the easiest movement that the structure can make when it hits with an earthquake. And that's actually, it sounds reasonable, like sometimes, okay, like definitely the easiest movement for a building is making something like this, right? And the second easiest maybe on the other way, depends, but this building is very thin. The thing is, it's not easy to make this movement because it's very stiff in this direction, but it's flexible in this direction because of the stiffness. There's no stiffness here, but there's a huge stiffness here. So this is the first movement. So when we say the natural period is the time that this building needs to make one cycle around itself, like goes this way, go this way, and come back to the original position. That's the fundamental period of the structure. Depends on what? Depends on the mass of the structure and the distribution of the mass, these masses, and depends on the stiffness of the structure, how stiff it is, okay? And also on C, we are including the damping, but I'm gonna neglect the damping right now. I'm not gonna talk about it. Let's talk stiffness, all right? But this structure has other movement. This structure can move like this. So that's not a natural period. We call it the second mode or the second period. Like, what is other options that the structure can move, can do movement. All right, so let's write them here. That's what the last thing that I did last time. We have, let's say this is mode shape number 1, and this is mode number 2, 3, let's put up to 4. Mode number 1 is the easiest mode, or the mode that means the shape, mode shape, the shape of the building that is gonna move. And the second is the second easiest. And by the way, actually, buildings sometimes have a torsional mode. They can torsion. It depends how easy he gets to this mode. Sometimes some building doesn't start with this mode. Like actually, it wants to start with this mode, but there's something in the stiffness that makes it twist. How? Like let's say that you have a building like this, all right? And there's a force F base coming from an earthquake is gonna hit this building. If this building has symmetrical stiffnesses, like has shear walls here and shear walls here, it's gonna move that way. But let's say somehow you cannot put a shear wall here. So what is gonna happen? This building, when it get hit with a force at the base, you wanna actually move like this, all right? And looking at the plan is gonna make like this. But the thing is, there's something very stiff is holding here. So what it's gonna do is gonna make like this. So the floor is gonna be like this, and it's gonna have torsion. So that's why, as a structural engineers, we need to find about this, something is called the center of mass and the center of rigidity. The center of mass is always at the CG of the slab. Like let's say the CG of the slab is here. That's the center of mass. Center of rigidity, where all the stiffnesses that contribute to the building. Like this part is very stiff. Like let's say if you have the shear wall here, I can imagine that the center of rigidity is the same at the center of mass, like here. But since this is not here, and we only have one, so the center of rigidity is gonna move a little bit down to this thing, so it might be here. But when the force of the earthquake hit, it always hit at the center of mass of the building. So when this happened, when you multiply this force with this distance, it's gonna give you moment. So it's gonna make a moment around the center of rigidity of the building. So it's gonna make the torsional movement. So this is just for your record. Okay, so let's get back to the moon shape. So let's find out, we have this is the easiest and the worst moon shape that I was talking about, but sometimes it's not. Sometimes it's torsion, sometimes it's something else. But let's say this is number 1, and this is number 2, and this is number 3, and this is number 4. This is a bunch of moon shapes. And I told you last time that the building doesn't only move with one mode. It's a combination of all modes. Some of them are very, very small that you cannot notice, and some of them that you can notice. Like if the building is moving actually this is not 100% of the movement is this. This is maybe 90%, and there's a bunch of mood shapes that contributes a little bit to this movement at the end, okay? And the mood shapes basically oscillate the mass in a way, the same way that the mood shape is moving. Like let's say, this one is gonna take the mass all the way here, but this one is gonna take the mass the other way. The contribution of both of them, by the way, they are not equally, like they are not contributing equally. Like this one is the 90%, 0.9, let's say that this is 0.05, this is 0.03, and this is 0.02. That's the 100% of the movement. 90% is coming from this mode, but you cannot see these because they are very small. So let's say this moon shape is gonna make a displacement at the top 5 centimeter. All right? And this one is gonna make displacement here like 3 centimeter. The thing is, you cannot say 5 minus 3. You need to multiply 5 by 0.9 and 3 by 0.05. So when you multiply 0.3 by 0.05, it's gonna give you 1, what is that, 3, 5 over 100, is gonna give you 15 over 100, that means 0.15. Can you imagine 0.15 centimeter? You will barely can see them out of the 5 centimeters. So that's what I'm talking about, that everyone has something, a percentage. This percentage is called the participating mass ratio, okay? So that's why I'm telling you for your record, like there's a bunch of mood shapes. So usually when we do structure analysis for structures, mood shape number 1 is the main thing. Some codes, they say if the contribution of mood shape number 1 is over 90%, like let's say that you made your building perfectly symmetric and there is no, the contribution from the higher nodes is very, very low. So maybe you can neglect that and you assume that all the movement is moving with mood shape number 1. Why we are doing this? Because at the end of the day, I want to calculate how much forces each story has. And the much of the forces depends on the mood shape. This one is going to give me negative force. This one is going to give me positive force. But anyway, let's keep it that way, that this is the mood shape of the building. And each mood shape has a period. Like, okay, like the time that this building need to go this, and come back to the original position, that's the T of mode number 1. This mood shape has completely different period. It's called T2 because this building to make like this and make like this and come back to the original position, that's different time. So each mood shape has a different period. Okay, so it has T2, T3, T4. Each mood shape is going to take different time to oscillate. All right, why I'm telling you this? Because the mood shape, as I told you last time, it's like the fingerprint of the building. Every building is having different fundamental grading. It depends on the mass and depends on the stiffness of the building. And last time I put the rule how to calculate this. All this comes from omega. Omega is equal to root k over n, and t is 2 pi over omega. So t is equal to 2 pi root the mass over the stiffness. That is the rule of the, so if you know the mass of the building and the stiffness of the building, put them here, you will be able to get which mass, this mass, and this is stiffness. The total mass and the total stiffness after you do all the summation. So keep this rule in mind, okay? And I told you last time, if the stiffness is high, the T is low. If the mass is high, the T is big. Okay, so I want right now to introduce you to a concept. It's called the response spectrum analysis. Let's go back to the first 5 minutes from our last lecture. I told you, we as structural engineers, when we solve buildings, we only interested in 2 things. We are interested in the internal forces in the building and internal stresses, but let's say internal forces, because if you have force, you can get stresses. And the deformations. That's what we do as a structural engineer. We get forces and members, and we get deformations. That's your job. If you got that, you solve the structure. If you know how much force in a structural member, you can, based on the material that you have, you can find a cross section that can resist this force. That's all our job. We take reinforced concrete, we take advanced mechanics of materials, a structural analysis to find forces, stresses. This is what we call a structural analysis. If you are gonna take structural analysis class or advanced structural analysis class, I'm teaching it next semester. So all what we do is we find the deformation in the structure and we find how much force is in the structure. What is the bending moment? What is the shear force? What is the normal force? What is the torsional force? We need to find all these forces.
When you say next semester, it's fall.
Yeah, it's advanced structure, but yeah, you have to have the basic structure analysis first. All right, so in structure analysis, that's what we do. But all what you did analysis to the structure. You only find deformation and you only find forces, but you didn't design the structure yet. To design the structure, all the designers have to do the analysis first, have to find what forces and what is the deformation. And if I'm a steel designer, I want to find the steel cross section that if this force is going to apply to, is going to resist this force. If I'm a concrete designer, I need to find the cross section that, second, I'm going to tie my shoes. If I'm a concrete designer, I want to find out what is the reinforced concrete section dimensions and reinforcement that is going to resist this force so that this building doesn't fail. If I'm a wood, masonry, it's all the same process. It's just different design rules. But structure analysis is the base for all the designs. For concrete, steel, wood, masonry, they all use the same structure analysis that we do because the process is the same to find the deformation and the forces, okay? What we do here is the same. We want to find the forces and the deformation so that engineers can take these forces and do design, okay? So that's actually what we are doing over there. So how we can make it to the engineers easy to find forces? All what we're talking about, right now I get U and I get U dot and I get U double dot. U is the deformation. That's one of the things that I would like. To be honest, I'm only interested in the maximum deformation that this building is gonna have. And I don't care if it's positive or it's negative, I only need the maximum, and this is the maximum. Why? Because I don't care about this small one. I'm caring about the maximum displacement that this building is gonna get. Small one is not gonna help me.
If it dips
If it's negative, it's the same. It just means that this building, rather than going this way, it's going this way. It's still maximum, even if it's negative. All right, so that's U. But the thing is, I already know U, but I want to know how much force is shaking the base. What is this F base? F base is the mass multiplied by acceleration. But by the way, this acceleration is not the ground acceleration. It is the structure acceleration. How much acceleration this structure is moving. So we need to find the acceleration of the structure. But the thing is, the engineers, I mean like in the codes, we don't want to do this process for every structure. By the way, we are engineers. You think that we love maths? We don't love maths. We don't love solving differential equations. We need something that is easy. Even that we are engineers, when I put a math problem, everyone's like, get mad. I don't know. We're engineers. We are doing math, right? But the thing is, it's a lot of work to do this as engineers in the offices to solve differential equations. So codes, sometimes it won't make it easy for the engineers to use curves to find forces rather than doing this stuff. So let me tell you what the engineers have done to make finding these values easy and not doing this. But actually what I'm gonna do is based on this. So let's see what they do. They developed a concept, it's called the response spectrum analysis, okay? Let's say that we have an earthquake, like let's say this is our earthquake, and this earthquake has a time history, AG, something like this. That's the earthquake that we have. We take this earthquake and apply it for many, many buildings, thousands of buildings. Some of them are real, some of them are artificial, many, many buildings. They take this earthquake and they put it for building number 1. And I'm gonna represent the building the same simplifications that we have. Mass and stiffness, K and M, all right? And by the way, I can put the building as K and M, or I can put the building as T, as T1. Why? Because T1 is one variable that is functioning in the mass and the stiffness. So rather than saying that building has mass M and K, building has a variable T equal to T1. So if you know M and K, you put them here, multiply them by 2 pi, you get the time. All right, so I have this building that has stiffness K1 and M1, so T has T1. And a second building has mass M2 and K2, and then it has T2. And they made the same process for many buildings until building that has mass Mn and Kn and definitely has Tn, alright? It's like, you know, like you are bringing an earthquake like this and apply it for a community like Miami or Los Angeles and see what each building is gonna respond. So that's what we're gonna do right now. We have an earthquake, it's gonna hit a community. Community has many buildings, tall, short, big, small, has different T's, right? Okay, so once you apply this, they solve this differential equation for each one of them. They put the mass and the stiffness and the damping and everything, and they get the maximum acceleration for each one and the maximum u for each one. So they made something like this. After they solve T, and let's put A, and actually you can put it as a U double dot. T and A, T and A, right? So once they solve the differential equation for each one of them, it gives them something like, let's say this one, something like this one, something like this, right? Every building is gonna have different response. They take the maximum response. That's the only thing that we are interested at, the maximum one. So where's the maximum here? This is the maximum acceleration that this building have. This is the maximum acceleration, either positive or negative, and this is the maximum acceleration that my building have. This is A1, this is A2, and this is AN for each one of these buildings. By the way, tell me the difference. What is the difference between this and this? What is this graph and what is this graph? Both of them are acceleration. This is the acceleration of what? The ground acceleration that comes from the earthquake. This, the acceleration of what? The building itself, right? Does every building is gonna have the same acceleration? No, like the tall building is gonna be different from the short, is gonna be different from, let me tell you, what do you think if a building is 50-story and a building is 3-story, which one is gonna have higher acceleration? The 50-story is long, it's gonna make a lot of displacement, but the short is like barely moving, right? Let's say we have two 60-story buildings. One of them is big and one of them is very thin. Which one is gonna have more acceleration? The thin one, right? It's like very flexible. So that's what I'm talking about. Everyone is having different one. All right, so we got the maximum of them. And next step, we are gonna build a relationship between the characteristic of the building and the performance of the building. And they call this curve the response spectrum curve. They put on the x-axis the t, the period of the building, and by the way, t is not only time, it represents stiffness. Because the t is coming from the mass and the stiffness, right? That's the characteristic of the building. I told you this is the fingerprint of the building. And they put on the y-axis is the response of the building, the acceleration, A. And they call it actually SA, the spectral acceleration. Why they call it the spectral acceleration? Or why they call this concept is response spectrum? Because we pick a spectrum of buildings that has different characteristics. This spectrum include tall, short, big, small building, and we are trying to find a relationship that can link all these spectrum of buildings in a relationship between the characteristic of the buildings and the performance or the acceleration of the building. So I have t on the x-axis and I have the spectral acceleration on the y-axis. What is I'm gonna do next? You are gonna pick the maximum acceleration corresponding to each t. So t1, the maximum acceleration is a1. T2, the maximum acceleration is a2, and you take the absolute because we're only looking at the maximum number, not negative or positive. And they try to plot it like something like this. And it gives them something like this. So when they tried to fit it this curve, it was something like this. But let me tell you something, this is only for one earthquake. One earthquake cannot cover all the possible earthquakes that's gonna happen. So they have a suite of earthquake, like maybe 10 or 15 or 20, and they did the same process for all the buildings again. The thing is, this curve is for just one earthquake. One earthquake was applied to a spectrum of building. They did the same process and brought another earthquake, and another one, and they did the same process again. Every earthquake that you use is going to give you another curve. Like another one is going to give you something like this, and another one is going to give you something like this, and they had many of them. That's how statistical analysis do. You have to have a lot of data so you can have an idea about, the general idea about what was going on, right? So some of these earthquakes are huge, that cause a lot of devastation, a lot of damage. There's many of them are known, like El Centro happens in California. I used to know many of them, but yeah, there's a bunch of them. And then they had all these curves, but the thing is, you cannot pick the minimum and you cannot pick the maximum, right? So we usually stick with the mean. So we got something, here's the mean, something like this, and something like this. And they had one single curve, and they call it the response spectrum curve. And it's a relationship between the natural period of the structure and the spectral acceleration of the structure. Then this is a general idea about the earthquake analysis. And basically right now, any building, if you know the fundamental period, if you know T of the building, and it's very easy. Softwares can calculate very easy. You just draw the geometry of the building, and it's gonna give you what is T is. If you know it, you can just go in the code in this curve, like this, and find what is the spectral acceleration is gonna be. Given the zone of the code, the thing is, the code has like all the information about the earthquake zone of the zone that you're working with. Like, let me put them for you here. Oh, I don't have it with me. Oh, it's over there. Yeah, so the codes do something. I'm not gonna ask you about this, but I'm gonna tell you just to know what's going on. So the code actually, it has a map, and in the map you locate where is your building at, like in Florida and Los Angeles. So you define something, it's called the seismic zone. And in the seismic zone, you are gonna get some parameters, and you define something, the risk category of the building. Like buildings that are residential is different from commercial. If you have a hospital, it has a risk category that is high, so you multiply by a bigger factor. So if you have a residential building and the factor is 1, you don't increase the forces. But if you have a hospital, you multiply by 1.5. So let's say that you calculate the earthquake force is like 500 tons. If it's a residential building, you're gonna use it the way it is. But if it's a hospital, you're gonna make it bigger, 1.5. If it's a nuclear facility, much higher. So that's what we call risk category. Then the code do some operations so that we can draw this responsive spectrum curve based on all these. I teach all this in the advanced structure analysis, but I'm gonna not teach it here. So I believe the last thing that I would say about the earthquake design, what I'm gonna do right now is just to simplify this, not what is actually being done, but it's gonna give you a general idea about the earthquake design. You get the SA, the acceleration of the structure, then you get the F base by multiplying the mass of the structure, multiplying by SA. There's many factors here, but I'm not gonna put them, like the importance factor, a lot of factors. And the thing is, when we use the mass, we use something, it's called the effective mass. Like we don't assume that all the live load are within the building. Like we assume maybe 0.5% of the live load or 0.25% of the live load. So that's what we put here. Once you get the F base, like once you know exactly what the forces that hit the F base, 500 ton or something like this, I distribute these forces on the stories in a way that can develop the deformation. Every story is gonna take a piece from this 500. How can I define this? It is based on the mass of the story and the height of the story from the ground. Okay, so this one is gonna take a force, this one is gonna take 1. The more higher, the more is gonna take from this force. And there is a rule that we can do this. So when we do analysis, as an engineer, I told you, we're only trying to find forces. Can you see all these 3 boards? I'm doing them to find the force that each story is gonna take from the earthquake. I wanna know the force at the base and the force at each story. So when I use a structure analysis software and I have my building, I apply the force at each story and then run my model, and then my building is gonna move. Once I have these forces, the software is gonna tell me, yeah, you have this force here, is gonna make a bending moment at the column here was like 5 ton meter. And the bending moment here is 2 ton meter. When you have a bending moment, as a designer, we put reinforcement so that it can resist the bending moment. Bending moments, do you guys have heard about bending moments before? In what class? Mechanics of materials. So bending moments is like if you have a cross section like this and it's gonna bend, bending moment is the enemy of the structure engineer. We don't love bending moments because bending moments are sneaky. Like they make tension and they make compression at the same time. The thing is, if my cross section is exposed to compression, I can put concrete. I don't have to put a steel because concrete is very, very good in compression. But if it's tension, I can put a steel. So if it's tension, it's good. If it's compression, it's good. So I know what I'm gonna use. But if it's bending moment, it makes tension down, compression up. So you need a steel down, and you need concrete on the top. So that's why we put like reinforced concrete, whereas the bending moment there is tension, we put the steel down. If it's compression, like let's say I have a beam like this, right? This beam, if it has a load, like let's say this beam has a load here and a load here, what is gonna happen? This beam is gonna bend like this, and then it's gonna go up like this, and it's gonna bend like this. That's how it's the bending moment. It's gonna have tension here, compression here, and then here it's gonna have tension up, compression down, and then here it's gonna have tension. So that's what I'm saying. It's a sneaky. It keeps changing between tension and compression. So the thing is, we put the reinforcement where's the tension at. So the reinforcement, when we do reinforcement concrete, we don't put like randomly. Like if there is tension, you will find most of the reinforcement here, and here there's minimal reinforcement. So maybe here you will find 10 bars, but here you will find only 2 bars. Here the tension is up, so you'll find most of the reinforcement is here, because here is compression. Concrete can take care of it. But if there's tension, concrete cannot do anything. If you didn't put reinforcement, the section is gonna crack. So the same thing here. I put reinforcement here. And by the way, look at this. The maximum bending moment is here. So we'll find that all the reinforcement lenses are not the same. So the more that you go to the maximum bending, you will find more reinforcement. So they make many cuts. Like they make some reinforcement goes from here to here, and then here you don't need that much reinforcement. You don't need all that reinforcement go all the way from here to here. Because here, the moment is almost zero. There is no tension. So basically you make less cuts so that you can save in the reinforcement. All this stuff you can learn it in the reinforcement concrete class. Same thing with when we design for earthquakes. If the building is not exposed to earthquake and all the loads are vertical, everything can be compression. Like you don't have to put every reinforcement in the columns because there's no bending moment. Everything is gonna be compression. There's no way that this structure is gonna go to the sky. Everything is gonna go down. All right. But if this building is gonna expose to earthquake, this column is gonna have a bending moment that way because you see all of them are making like this. So you need to design this column to take the bending moment, but also in the other side, the column is gonna have bending moment too. So you will have to put reinforcement all the way so you can resist the bending moment in X and the bending moment in Y, and also the axial load. So basically, columns in earthquakes, if you look at the columns, something like this, they have compression like this, B, coming from the loads that they take from all the way up to down, and this is, let's say that this is X and Y axes, something like this. They have a bending moment around this axis and a bending moment around this axis. And this bending moment, it makes tension here, so you need reinforcement because it's like this. So pull this and compress the other side. So you need reinforcement here, and this one, you need reinforcement here. And we always design for positive, negative moment. The thing is, yeah, this earthquake might be this way, but actually it might make another moment another way. So the reinforcement that you have here, you put something similar on the other side. That's why you find all the way around. And even if the column is having just a pure axial force. Sometimes we put reinforcement so that it can both the concrete and the steel can take the load. Like we distribute the load between the steel and the concrete. All right, so that was like a brief introduction about seismic engineering. That's not everything. I did a lot of simplifications here. That's not everything. Like this one doesn't work that way. There's matrices, there's a lot of stuff that we do here. But I give you an idea how seismic analysis for building work, and this can help you to start the main course. To dive in deep into this science, you have to take a class. It's called structural dynamics. I believe the chair of the department teach it as a graduate class. And then once you have a full idea about structural dynamics, it doesn't have anything from the dynamics that we taught. Like it has this. He's gonna spend the whole semester explaining how to get all these. Can you see the 30 minutes that I have done? He's gonna spend the whole semester explaining this. Like one lecture talking about this system, maybe 3 lectures, solving this system. Another 2 lectures, solving this system. And another maybe 3 lectures or 2 lectures, defining the responsive spectrum system. But what I give to you is a summary, how to do this in summary. And then once you finish the structural dynamics, you get to the design. So all the course of structural dynamics is gonna get you to calculate the forces. Then at this, you are gonna stop. You're not gonna do any design. That's a structural dynamic, because structures, we don't care about design. Designers can take this and design a steel structure, or design wood structure, or design a forcing concrete structure. So he's gonna stop at the forces, and then if you wanna know how to do seismic design, you need to take a class. It's called seismic design. You see how to use these forces to get reinforcement, to get cross sections, and to do all these stuff. Definitely, if you want more, like if you want to dive deep in design of tall buildings, you have to take a tall building class that teach you how the tall building systems look like, and how we analyze them, and how we use software to do them. And also I do a little bit of this in the advanced structure analysis class as a whole. All right, does anybody have any questions so far? Is it interesting topic? Do you guys like it? Do you guys want to be structural engineers? Okay, good. With this, I'm gonna spend the next 30 minutes introducing. So right now, let's see what we covered. We finished the particle dynamics, chapter 12, 13, 14, 15, 4 chapters. We got tested on chapter 12 and 13 in midterm 1. We got tested in chapter 14. No, we didn't get tested. It's gonna be Tuesday. You are gonna get tested on chapter 14, 15, and the fluid dynamics part. So we finished particle dynamics, fluid dynamics, structural dynamics, and what we are gonna do in 1 minute is called rigid body dynamics. Okay? All right.
Question.
Yeah.
For the upcoming test, what you would say is the average of the difficulty of the questions you're going to put?
From my perspective, it's easy. It's the same difficulty from last year. I'm not gonna increase it. And actually, the students from last year, they did very well in the second exam. And I hope that you guys will do as well. Maybe they did also a little bit bad in the first one. I understand. That's why I make 2 exams, so you have 2 shots. So I hope that you guys will prepare, try to study very well, and it's gonna be the same difficult. And from my perspective, it's not difficult at all. It's the same problems from my class, even like less difficulty. Like at least you should be able to solve a system, an inclined system. Like if you have something like this and a body's moving on a slope, you should be able to do it. If this body is attached to spring, you should know how to deal with the spring, how to get the energy of the spring, how to know the potential energy of the body, select a datum and measure the body from the datum, the final compression in the spring, like the initial stretch and the final stretch. All this stuff you have to do it on your own. Impulse and momentum, I solved a problem that has a wall, that has a body that hitting a wall. You should be able to fix all the walls and the body, or 2 bodies is hitting each other. Impact. You should be able to do this. I'm not gonna give you a crazy problem, but at least you know how to solve the one in the notes. I don't even do the complicated problems in the homework. I know that you guys, some of you don't solve the problem, the homework in the on your own. That's why the homework only have 5%. Okay, so at least you do the class problems. Okay, so that's what I'm asking, right? And you'll understand them, not memorize them. It's not gonna be the same problem. It's gonna be different idea. So you have to think. Okay. All right. You guys want to take pictures of this? Because, by the way, the exam is not solving a problem. I'm going to ask you to describe a process. Describe how a building can be converted to multi-degree of freedom, to single degree of freedom, to write the equation of the motion, the solution of the equation of the motion, the response spectrum analysis method. Maybe I'll ask you to describe this process. How the response, this is for the final exam. How to do responsive spectrum analysis. We have a ground motion of an earthquake, we apply it to a spectrum of building, we get the responses of the building, and then we draw a responsive spectrum curve. Okay? All right, so well, I think maybe I would start next lecture. I'm gonna give you guys this 25 minutes of freedom to enjoy, and I'm gonna feel bad about it, but I'm gonna start the rigid body dynamics next lecture. I think you guys had an overdose of seismic, so let's close it that way. And you guys can, maybe after the midterm, we're gonna start the rigid body dynamics, and then I believe I'm trying after the midterm on Thursday to have our field visit to the wall of wind. So I'm gonna confirm with you on this. Okay, see you guys next week.